You've now gone through the idea of modular arithmetic, and inside this modular arithmetic we have something called rings, specifically integer rings. What it represents is the list of integers. Okay, and a simple example of it would be, okay, the list of integers we represent it like this. Let's say all the way to m. Now the boundary is what matters, because rings, just like the ring, well, it is bounded. So if you look at a clock, we have 12 here and it goes to 1 and so on, right? It reaches 11, 12 and then back to 1. So the idea of the ring states that it is finite in nature, and in our case is integers. So let's assume my m is 9, which means it will be 0, 1, 2 all the way to 8. Okay, this is going to contain 0, 1, 2 all the way to m minus 1. Okay, this is a ring. And so if I try to formally define it, okay, the integer rings consist of, number one is the set of integers, okay, from 0, 1, 2 all the way to m minus 1, and 2 is the operation, okay, the operation of plus and multiply. For all, let's assume we have some elements from here, so let's say a, b, c and d. Given it belongs to this ring, such that we can perform a plus b equivalent to c mod m. In our case, for this example, the m would be 9, right? And another one would be a multiply b is going to be equivalent to d mod m. That is, a multiply b, okay, when you divide it by m, should contain the remainder that's within the ring. So this is, roughly speaking, a formal definition for this integer rings. So let's look at an example. Okay, so let's assume our m is 9, okay, which means in this scenario we're dealing with a ring of m from 0, 1, 2, 3, 4, 5, 6, 7, 8, right? The m is 9, the last one is m minus 1, so it is up to 8. And now to use this as an example, a plus b, let's assume we have 6 and 8. This is part of the ring, okay. This is equivalent to a remainder mod m. In our case, the mod m is 9. Now what would the remainder for this? So 6 plus 8 is going to be equal to 14, so this is 14, and now 14 divided by 9, the remainder would be 5, and this 5 should fall inside the ring, just right here. Another example would be, let's multiply it, okay, 6 times 8, which is in our case 48, right? So this is going to be equivalent to something mod 9. So 48 over 9 is 9 5s of 45, so the remainder is 3, and this 3, well, you guessed it, it falls within the ring. Okay, let's look at some other properties of the integer rings. So they are, one is we can add and multiply, okay, two numbers, and the result is within the ring, so in this case the ring would be called as a closed. Okay, ring is said to be closed. So we can add and multiply two numbers, and the result should fall within the ring. Another one is it possesses a property of associative. Okay, both the addition and multiplication are associative. What it means is, given that we have this A, B, and C, let's assume that they fall within the ring. So we will get the property of associative in both addition and multiplication. That is, let's say we have A plus B plus C should be equal to A plus B plus C. Well, it's pretty straightforward, but also the same thing applies for multiplication. So A times B times C, okay, is going to be equal to A times B times C. This is another property for this. The third one says that there is a neutral element, well, neutral element of 0, okay, with respect to addition. With respect to addition. So that is, given that we have, let's say, all the elements of A that belongs to the ring, right? It holds that A plus 0 is equivalent to A mod M. Okay. Now, well, you guessed it, M is going to be the highest value. So in our case, let's say we considered M and above. In this specific ring, we considered M to be 9. So M is higher than all the elements that's been here. See, the maximum value we have here is 8. M is the highest one, which means, well, what this reads as is, this is A over M, okay, should give us the remainder of A. And you guessed it, so if we're dividing anything by a bigger number, the remainder would be this number itself, right? So this A would be our remainder. Okay, let's look at another one. For any element A, let's assume A is in the ring, okay, A in the ring, there is this negative element, okay, we have the negative element, let's call the opposite of A, okay, negative element of negative A, such that A plus the negative A, okay, is going to be equivalent to 0 mod M. And rightfully so, I mean, we're talking about 0 being equivalent to 0 mod M. Well, when 0 is divided by M, we get the answer to be 0 on the remainder as well. Okay, now just like this addition, we'll also have another property for multiplication, which is similar. Only difference is, instead of 0, we'll have 1. So that is A times 1, given that A belongs within the ring, A times 1 is going to be equivalent to A mod M, right? Well, what it means is A times 1 is going to be A. So A over M, it should give me the remainder of A. So let's look at another property, and that is this multiplicative inverse. So the multiplicative inverse exists only for some elements. So that is, let's say we have this A that belongs to my ring, okay, the inverse of A, well, the inverse inverse of A, that is A inverse, is defined as A times A inverse, okay, is equivalent to 1 mod. Okay, now you might be wondering, is a multiplicative inverse. For example, if we have A to be equal to 2, inverse of A is going to be obviously 1 over A, right? There is going to be 1 over 2, 0.5. Well, 2 times this 0.5, that's going to give me the amount of 1, given, let's say, the m is 9. This is totally wrong. Okay, see, it turns out this inverse of A, in our case we've written it as 0.5, but this does not belong in the ring. So this inverse of A would also fulfill the fact that it belongs to the ring. So we had the rings, let me write the rings that we had. So the rings of this 9, right, is going to be 0, 1, 2, 3, all the way to 8. Now we don't have a decimal number here, so this does not belong to the ring. For this property to even exist, the A inverse should also be part of the ring, and this is our formula for this. So it's going to return the remainder of 1 mod 9, which means what is the inverse of A in our case here? So given that A is 2, what is supposed to be the inverse of A? Well, we can just compute it. So let's assume here A is here, A times something. Okay, it's going to give me the remainder of 1 mod 9, which means A times something divided by 9 is going to give me the remainder of 1. So so 2 times 5 is going to be 10, right? So 10 over 9 will give me the remainder of 1. So in our case, this would be 5. So 5 is the inverse of A. So this is A and then the A inverse, okay, of this 1 mod 9. And it turns out there's a technique to understand if the inverse even exists or not, and that is the Gcd technique. So the greatest common divisor of A, and let's say this m, okay, so if that Gcd is equal to 1, then the inverse exists. Okay, otherwise it does not exist. The example where the inverse may not exist would be, so let's assume my A is 6, my m is 9. So in our case, the GCD, the greatest common divisor of these both is 3, right? So the factors of 6 is 1, 2, 3, and 6 itself. For 9, we have 1, 3, and 9. So 3 is the greatest common divisor. Now, it does not fulfill this property, okay, of this GCD of A and M being 1. So in our case, it's 3. So in this scenario, 6 does not have the inverse, okay, does not have the multiplicative inverse. So we can never write 6 times the 6 inverse is equivalent to 1 mod 9. This is wrong.